So it's 8 o'clock now, so I will start. And so first of all, can everyone confirm that they're seeing a screenshot of just a PDF?
Yeah.
All right. Okay. So yeah. So this is my second lecture and the third week. And so this lecture will be on combinatorics. So today the lecture will be on today the lecture will be on binomials. Okay. Binomials, counting with recursion, probability, and expected value. Okay, sorry. Yeah. Okay, yeah. So binomials, counting with recursion, probability, and expected value. All right. So with that said, this is our first problem. And so as usual, if you ever get an answer, please private message me. And if you ever have any questions, just somehow make it known in some manner. I'll start going over this problem now. So for this one. So for every subset T of this set of elements U from 1 through 18, let, let S of T be the sum of the elements of T with S of the sum of the empty set being 0. And so we want to basically find the probability that S of T for some random T is divisible by 3. So what we first notice is that the fact that the numbers are from 1 through 18 doesn't really matter. What really matters is that it's just 6 numbers and the remainders are 6 triples of numbers where the remainders are 1, 2, 3. So all in all, there's 6 numbers of remainder 0, 6 of remainder 1, and 6 of remainder 2. And so now with this, we can use what's known as a generating function. Now, the concept for a generating function is basically, we find something, we basically look, so the way this generating function in particular works is basically we look at the exponents. So as you can see, in this first pair, we have 0 or 0. And what that means is that if we choose not to include this number in the sum, then the remainder when divided by 3 will change by 0. And if we do choose to select it, then the remainder will still change by 0. And the second pair, where it says x0 and x1, that basically states that if we choose, basically states that if we choose to include it, then our remainder increases by 1, and otherwise it will stay the same as 0. And the same applies for the final pair. And so clearly we need to raise all of 3's 3 to the 6th power. And that's solely because there's 6 numbers of each of the remainder. And also we will just define this as f of x. And that's just for the sake of convenience when writing it later. this f of x part. Although generally generating functions are given f of x or something of the sort. So now what we want to find really is just the sum of the coefficients of all terms of the form x to the power 3i, where I is some integer. So, yeah. And so, now what we can do next is apply the roots of unity filter. So what the roots of unity filter is basically, for the case of 3, it's simply just finding the sum of f of 1 plus f of omega plus f of omega squared, where omega is equal to e to the 2 pi I over 3. And so this works because if you look at the binomial coefficients, when you expand everything out, you'll see that actually the only things left are of the form x to the 3. And you need to divide by 3 because each of the coefficients are counted 3 times. And so, yeah, so you just, from here, just plug in 1 omega and omega squared, and this is what you get. And here, this step is slightly abbreviated because there's little space left, but actually it should be something like 2 to the 6 times 1 plus omega to the 6 times 1 plus omega squared to the 6. So this is f of omega, and f of omega squared is 2 to the 6 times 1 plus omega squared to the 6 times 1 plus omega to the 6. But these are just equal to each other. So in here, it just got abbreviated. All right. And so after that, you can just see that this expression is just equal to 1. So this is equal to 2 to the 18th plus 2 to the 7th divided by 3. And so now we want to find m. So although this is the numerator, it's not m yet, because we're given that m and n are relatively prime positive integers. And so currently, so if we ignore the fact that m and n have relatively prime, the answer would be the numerator in the numerator to sorry. Okay. So in the numerator, it would be 2 to the 18th plus 2 to the 7th divided by 3. And the denominator will be 2 to the power of 18. Because that's the number of possibilities. And so basically, in order to simplify this, all you need to do is continuously take out powers of 2 from this number. And, well, you can just see that there's a total of 7 factors of 2 in the numerator. And so once you cancel that out, the numerator is simply just 2 to the 18th plus 2 to the 7th over 3. And that's equal to, sorry, not equal to, but goes to. So the initial numerator is 2 to the 18th plus 2 to the 7th over 3. And then goes to 2 to the 18th, 2 to the 11th plus 1 divided by 3. And if you calculate this out, this is just 680. So the answer to this question is that m is equal to 683. Okay, so if there are any questions, please ask, and if not, you can go on to try this next problem. And once again, you can private message me answers or ask in any manner any questions. All right, so I'll go over this problem now. So let n be the number of positive integers less than or equal to 2003. They're less than or equal to 2003. and their basic representation has more ones than zeros. And so we want to find that. All right. So first of all, the leftmost digit is clearly going to be 1 in any binary number. And I'm just going to refer to basic representations of numbers as just their binary form. And so that means that there are n choose k numbers that have n plus 1 digits and k plus 1 ones. Because we already have that the leftmost digit is 1, so there are only n digits left and k more ones. And so that means that for there to be more ones than zeros, that would have to mean that k plus 1 is greater than n plus 1 over 2. And so that would imply that k is greater than n minus 1 over 2, or k is at least n over 2. So, so basically, this is the sum of all elements in the right half of the periodic table, and that includes the middle terms. And so, in order to find this, we can basically, one way is to find the sum of the entire periodic table, then add the, okay, hold on. Okay, when I said periodic table, I meant Pascal's triangle. Okay. Okay, anyways, excluding that mistake, basically, to find the sum of the right half of Pascal's triangle, one way you can do it is to find the sum of the entire Pascal's triangle, well, up to the 11th row. And that's because after the 2003 is between 2 to the 10 and 2 to the 11. So we just stop after the 11th row. Or you can also count it as 10th row, but just the 11th row, if you count the very top row, that's just a single one as row 1. So yeah. So we want to find the sum of the numbers there, and then add on the sum of the numbers in the middle, and then divide by 2. And that's one way to find the sum of all elements in the right half of Pascal's triangle. And so the sum of all elements is just 2047, and the sum of all the numbers in the middle is the sum from 0 to 5 of 2i choose I. And you can just see that the numbers are 1, 2, 6, 20, 70, 252. And their sum is 351. And so we want to find the sum of these and divide it by 2. And so this number, the end result is 1,190. And we're not done yet, and that's because we need to see that the numbers are less than 2003, not 2047. And so also, all the numbers from 2004 to 2047 work, and that's because there's already enough ones in there that there's already more ones than zeros in all of them. And so they all count, and that is the total of 44 numbers. And so we need to subtract that number from 1,199, and so we get 1,155. And so we wanted n mod 1,000, so the answer is just 155. So that's it for the binomial section. And so now, once again, if anyone has any questions, please tell it to me in some way. And if not, you can try this problem on your own and private message me if you get an answer. All right, so I'll start explaining this problem. So the figure below shows a ring, and it's made of 6 small sections, and you are going to paint them. Basically, there are 4 select colors per ring. 4 possible colors, and each section of the ring will be a solid color. And so you want to find the number of ways you can paint them if no 2 adjacent sections can be painted with the same color. And so to do this through recursion, and so you can let there be n sections. And so we can first find an for small n. And so a1 is equal to 4. A1 is 4, A2 is 12, and A3 is 24. Okay. And so now for n greater than or equal to 4, so a of n is equal to, so first of all, we can just assume, for instance, that it goes something like blue, green, pink, yellow, red. So in this case, there are 2 choices for what can go here. 2 choices, and they are blue or pink. And so now the number of ways to do this is simply just a of n minus 1. And then after that, we need to multiply by 2. But on the other hand, this does not account for the case where it goes like yellow, pink, yellow, green, pink, red, yellow, and something else. And here it can be green, red, or pink. And you don't know for sure. And you only know these 2. Sorry, these 3. So that's why the sum is 2 times an minus 1 and 3 times an minus 2. Because there's 3 ways here where that rather wide arrow is pointing. And at the same time, there's a of n ways, because after that, this one would have to be this. So, yep. And so after that, we can just start bashing it out. And so A4 is 84, A5 is 240, and so A6 is 732. And so that's our answer, 732. So, yeah. And so, if there are no more questions, well, then I'll just go on to the next problem. And for the sake of being able to go through all the topics with the time we have, I will just skip this problem. So the next one is on probability. So yeah, once again, if you have any answers, please private message and ask any questions that you may have. All right, so now I'll start explaining this problem. So there are 6 men and some number of women. So for rather obvious reasons, we will just write we will just let there be MW woman. And yeah. And so let P be the probability that a group of at least 4 men stands together in the line, given that every man stands next to at least one other. And so, doing this, want to find the least number of women such that P is at most 1%. So yeah. So now, if all the men are next to at least one other man, that means that there's only a few possibilities, and they're listed here. So either all 6 men are together, or it could also be that, sorry. So it could also be that all 6 men are together, or 4 and 2, or 3 and 3, or 2 and 2 and 2. And so we can just directly apply stars and bars here, and what we can get is that, so this in respectively in order they are, and so yeah. And so if there's a group of at least 4, then that means it must be either a giant group of 6, or a group of 4 and 2. And so this is just W plus 1 choose 1 plus 2 times W plus 1 choose 2, all divided by W plus 1 choose 1 plus 3 times W plus 1 choose 2. And this is, and plus W plus 1 choose 3. And so this all simplifies to 6W plus 6 over W squared plus 8W plus 6. And so, and so this is almost 1%. And so we can see that if we eventually calculate this out, what we can get is that W is equal to 590. And so that's the answer to this question. So does anyone have any questions? Okay. Well, anyway, so let's move on to the next question. And so once again, if you have any questions, please ask. And if you have any answers, private message. All right, so I'll start going over this problem. So in a game show, there are 7 doors, and there are 7 doors, and 2 of them have prizes. 7 doors, and 2 of them have prizes. And so after Bob chooses a door, the host opens after he chooses door. So the host opens 3 other doors, and one of them is hiding a prize. And so obviously Bob cannot switch doors to one that is open. And so Bob chooses to switch to another door, obviously one that's closed. And so what's the chance that his new door, is hiding a prize? Okay. And so basically if Bob's initial door has a prize, then switching will not give him anything. Then switching Bob is guaranteed to not have a prize. Oops. Okay. If Bob's initially door has prize 1. So yeah. So if the neutral door has a prize, well then his swap won't give him any more. Oh dear. Okay. So now there's a 5/7 chance that Bob didn't have a prize initially. And of the three doors, each of them are equally likely to have the prize. So there's a 1/3 chance of a prize. And so that means that the answer here is 5/7 times 1/3, which is 5/20. All right. Yeah. So if you don't have any questions, then we can just move on to the next problem. And so once again, if you have any questions, please ask. And if you have any answers, please private message me. All right. So I'll start explaining this problem now, and it'll also be the final problem for today. There's one more problem down here, but there's not enough time. So, but on the bright side, we did manage to get through at least one problem from each of the topics. So, Freddy the Frog, he's jumping around the coordinate plane, and he's searching for a river that lies on y equals 20. And there's a fence at y equals 0. And so in each jump, Freddy randomly chooses a direction parallel to a coordinate axis and moves 1 unit in that direction. So you can either go 1 unit in the you can either go 1 unit up, down, left, or right. And they're all equally likely. And so if he is at y equals 0, then it's with equal likelihood that he chooses which of the 3 directions to jump. And he will never choose to jump over the fence. And so Freddy starts to search at 021 and will stop once he reaches the river. So we want to find the expected number of jumps it will take Freddy to reach the river. So this problem is going to be solved by using expected value in states. And so the way this works is basically we're going to consider the different states that are possible in this problem in some way. And then we will form equations based on those states. And the answer will also be the answer and initial condition are also usually one of the states. So yeah. So from xy, okay. So from xy, so we can say that there need ay jumps to the river. And we can say A24 to be 0, and that's because 24 is the location of the river in the first place. So after that, so for A0, you can see that there's a 2/3 chance that it goes to A0 again. So we would put that as 2/3 times A0 plus 1. And the reason for the plus 1 is simply just because Freddy has made 1 move. And so yeah. So and the other chance is that Freddy moves up and into A1. So it's a 1/3 chance of A1. So yeah. And for the rest of the numbers, we can see that I can't really highlight that using yellow. Okay, let's use this color. Okay, it's not helping much, but I guess it'll do. So yeah, so a of n for everything else is 1/2 times 1 plus an, and that 1/2 is from jumping left to right. And there's a 1/4 chance of 1/4 times 1 plus an plus 1. And this case comes from the chance where Freddy jumps upwards. And obviously the final case would be if Freddy jumps downwards, which would be 1/4 times 1 plus an minus 1. And so we can see from this first equation that it just simplifies down to a1 is equal to a0 minus 3. Excuse me for a second. Okay, so sorry about that. Anyway, so yeah, so from the first equation we get that a1 is equal to a0 minus 3, and the second equation simplifies to an plus 1 is equal to 2an minus an minus 1 minus 4. And so actually what the second equation implies is that the difference between consecutive values of ai increases by 4 for each time the I itself increases. So what this means is that a2 is equal to a1 minus 7, a3 is a2 minus 11, and so on. And so this means that a21 is equal to a22 plus 87 is equal to a83 plus 91 plus 87 is equal to a24 plus 95 plus 91 plus 87. And so a24 is 0, so we can ignore this. At this point, we can just ignore this. And so 87 plus 91 plus 95 is simply just 273. And so that's our answer. And so that's it. And so I guess that's it for today's class. So there is this problem, but it's already 9:30. So yeah, we can stop here. And so thank you for coming to class. And I hope all of you, I wish all of you a nice rest of your weekend. So thank you and goodbye.